So another thing we're going to look at is relative minimums and maximums, and this kind of goes with your increasing and decreasing intervals. Suppose that f is a function for which f of c exists where for some c in the domain of f. So basically we're saying we're making sure we're in the domain. F of c, so your y value, is a relative maximum if there is an open interval around c such that what we see is that f of c is the largest point in that little small interval. And that's for all x in that area. A relative minimum means f of c is a relative minimum if there exists an open interval around your point c, in which, this case, we see that f of c is going to be smaller than all the values around it. Your relative minimums and maximums together, we call them relative extrema. So when we talk about relative extrema, we're talking about relative minimums, relative maximums. There's another set of minimums and maximums that are global. We're not worried about those ones. They're just the relative ones. So relative minimum maximum values. Another way to describe these is as follows. The location of your relative minimum is a point where your function changes from increasing to decreasing. Let's say we had a graph and we're doing something like this. This point's a relative minimum. This is where I went from decreasing to increasing. So that is the location. The value of the function, so your y value at that point, is what we call the relative minimum. A local or the location, sorry. So we also call these locals, relative local minimums and maximums. The location of a relative maximum is the point where we go from increasing to decreasing. The value of the function at that point is said be the relative maximum. So once again, what is the y value? So if you go from decreasing on one side and then you start increasing, that tells us we have a minimum. If we're increasing on one side and then we start decreasing on the other side of that point, that is the location of a maximum. So just an example again, this would be a relative maximum, that's a relative minimum. So notice that only talking about where I go from increasing to decreasing. A function can have multiple minimums or maximums, or only a minimum or only a maximum, or it can have neither at all. So if I line like this is an exponential function. I don't have any kind of local extrema. Like I said, I keep saying local because usually we say local instead of relative. Your book just uses relative. So we have no relative extrema. These examples, I have just a minimum. So sometimes you, like I said, you could just have one or the other. This one has a maximum and then a minimum. This one has two minimums and one maximum. So you can't have multiple of either. So I'm going to use those same graphs again. I want you to tell me what is your relative minimums and maximums and where they occur at. So what I'm asking for essentially is this part's your input at that point, or your x value. This graph is in t. So these would be your x's and these would be your y's. So the minimum or the maximum refers to the y value. That refers to the y value. And the location is just going to be that x value. Those tend to get a little confused, but like I said, location is just the X, and then what is the minimum, the maximum, that is the Y value at that point. So if you could take a minute on 3 and 4, just find me those minimums and maximums, and then come back. And then number 5, I forgot about that one. Number 5 is an application problem. Take a stab at that one as well. So that one is using the idea of minimums and maximums to try to find a maximum, I believe, a garden space. Okay, so we had 3 extrema here. This one was going to be one of your minimums. So the location of this minimum is here at 1. Like I said, we had a t-axis, so but same idea as x. Then what its y value is, that is the relative maximum. So this is a point at 1, -1, location. And then this is your minimum value. This third point, that's going to be a maximum, so we're going to put it down here, but that one is a ordered pair at 3, 1. So the first part is the location, so it occurs at 3, but that relative maximum is 1. And my last one here occurs at 4 and maybe 1/2. So the locations at 4, what the value that minimum is that y value, that 1/2. If you look at this one, remember the minimums and maximums occur from when you change from increasing to decreasing or decreasing to increasing. So we really just have the 2 of them. This is not an extrema. It is not a value larger than the ones around it. So this one would be our relative minimum. And as we see, this is going to occur at x is 0, y is 1, 2, 3, -3. So the minimum is -3, and it occurs when x is 0. The maximum's here at 6, 4. So the relative maximum is 4, and it occurs when x is equal to 6. All right. And this was the application problem. And if you struggle a little bit, that's fine. Just give you a chance to try it. So a man plans to enclose a rectangular area using 80 yards of fencing. If the yard is WY, we want to express the closed area A as a function of W. So we have 2 things here. We got this area that we have to fill in. We know that the boundary, all this fencing that I'm going to use here, should equal 80 yards. So if I add up all my sides, make those obviously L's, that should equal 80. So 2W plus 2L equals 80. Now, what we're interested in is area, not parameter. We know area is length times width. We want to express this as a function of W, so this is where we're going to use some substitution techniques. So if I solve this equation for W, 80 minus 2L, I'm sorry, solve it for L. We'll see why in a second, but I want to be just W's, so I'm going to solve for L here. So 2L is going to be 80 minus 2W. If I divide everything by 2, L is going to be 40 minus W. So what we can do now is that I can use this to replace L. So we've got 40 minus W squared. So what we're going to do here is we know how to find a maximum area. I think part of this got cut off. If we want, so this is the way to express it as a function. Now, if we want to find the maximum area, all we'd have to do is just graph this and then we can see what the maximum area is. Made a little typo here. I'm distributing this W across, so this would have been 40W minus W squared. All right, so I'm using Desmos, and Desmos, I have to replace all my variables with X and won't take the W very well. So I made it 40X minus X squared. So if we expand out, we see right up here is my maximum value. So I have a maximum value. Let me click on that again. Of 20, 40. So remember, this has to be my X and this is my Y. So we said X was that W, our width, and what we were looking for was area. So my maximum area would be 40, I think we were in feet, 40 feet squared. And that would happen if W was 20 feet. Okay, so we can figure out the dimensions of this garden now. Like I said, we know combined, this is supposed to be 80 feet. If I put 20 here, 20 here, that takes away 40 feet. So now I'm left with 40 left over. I have to split between these two sides. So actually the maximum area would actually be a square. But this is why we care about maximums, is they help us solve certain kinds of problems. So like this one here, I had a formula for my area. Well, I could use that to figure out a maximum because I can look at my graph, tell you where that maximum is. And then from there, I can get the dimensions that I need for the maximum area that I need to cover.